Hey guys, welcome back. I'm super glad to see you here. It's Jacob, like always. Today I want to start going over some basic concepts of how electronics work. The first thing that I want to go over with you guys today is the full bridge rectifier, and this device can convert alternating current coming out of your wall into direct current that devices can use. Things like phones, cell phones, Bluetooth speakers, or speakers that you would plug into your wall. Things like external battery packs to charge your laptop. A laptop uses direct current, and various things like this. Many devices use direct current. In fact, any device that has a battery uses direct current because batteries are direct current. So if you guys are interested to see how this works, then stay tuned and we'll take a look at it. So bear with me here, guys. I really hope this is an okay camera angle for you to be looking at the schematic. If it's not, I will notice when I'm editing the video and I will apologize. My tripod is only 6 inches tall or so I'm very limited as far as that goes. But without further ado, let's go ahead and first of all take a look at the boring part here. We got to take a look at a schematic to see what we're working with. Well, let's start with the device. So this is the device that I have come up with here. You can see I have a fuse for protection. You could never have too much protection. And then we have these diodes here which block certain directions of the alternating current. Let's see here. Then we have the once the alternating current has been filtered, you could say, the correct term for it is it would have been rectified. So it is no longer alternating. It is now direct, positive and negative, and but this is the device that we're going to be looking at here today. So let's go over some of this theory here. I have the schematic drawn up here, but for the sake of simplicity, let's go ahead and take a look at the first part here. A transformer. I have wired up the 120 volt side to a plug I can plug into my power strip that I have up here. And out this side here, I get roughly 20 volts. And so I can plug this directly into my breadboard and use the voltage that gets transformed through this transformer. But once it comes out of the transformer, it is still alternating current. A lower voltage and easier to work with, but still alternating current. So to fix that, we build the rest of the rectifier. So this here is our alternating current transformer, and you can see the winding for the primary coil and the winding for the secondary here. Alternating current, the term alternating current means what's coming out of your wall, you have a neutral and a hot line. The neutral line remains 0 volts at all times. The hot line alternates between positive, so it rises up to 120 volts and then falls down to 0 and down to negative 120 volts, rises back up to 0 volts, and then continues the cycle up and over again. Now this is useful for many applications. In fact, alternating current is easier to transport long distances, easier than direct current, but that is theory that I don't want to get into here. The primary point of this is to show how to convert alternating current into direct current and the difference. So, in order to convert this alternating current, we would have to stop it from going from this positive up here down to this negative down here and then back up to this positive. We would want it to remain positive on one side and remain negative on the opposite side. So what we're going to have to do is we're going to have to either get rid of this here or somehow convert it to a positive bump here. So we would get a positive and a positive and a positive. Now the only problem with this is that you're going to have this jolt from 0 volts all the way up to 120 and then back down to 0 volts, and then it's going to jump back up again and then back down to 0 volts, and that's going to happen 120 times in a second. Because so from this point where it rises from 0 up to the peak and falls down to its lowest point and then comes back up to 0 again, this is one full wave. And we want to, quote-unquote, rectify this. And so we want to somehow convert this up and invert this so that we have this bump here. Alternating current, 120 volts in the United States coming out of the wall is at a rate of 60 hertz, which means 60 times a second. So when you convert this to this bump here, now you are doubling essentially how many times it happens in a second. So you can see bump, 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 and so that is now being multiplied by 2, which is now 120 times in a second. But that's okay, that's not a problem. The only problem with this is, if you try to power something with this, first of all, 120 volts, there's not a lot of DC applications for 120 volts. And second of all, you're going to have this drop down to 0 and then back up to 120. In fact, there are some peaks in here that actually go up further to 160, and we'll take a look at that here in a minute. That's why we have some filters on our circuit. But we want to get rid of this. This is a no-no. We don't like this. We want it to be a constant voltage and then constantly 0. We want to have this constant. We want to have it directly, a direct current. That's what we want here. And that's what we are trying to do with this schematic here. So, to start off, we have our alternating current coming through this winding and being transformed down to 18 volts. And the way that this works, the way that a transformer works, it uses a magnetic field around an iron core, and when you wind some type of conducting wire X amount of times, and you wind another wire X amount of times, they will actually transfer electricity without touching each other. And when you have an iron core in the middle, so let's take a look at this. When you have an iron core in the middle, it assists in the electromagnetic field and in the electron transfer from one wire to the next. And it makes it more efficient, and it makes it much easier, and it provides a nice housing for all of the wires, so it works out great. There's more theory behind this. That's a basic breakdown. I don't need to go deeper than that. Basically, you just need to know that 120 volts is coming in here, and it's alternating back and forth, positive, 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 positive. And it's going through these windings back and forth, changing the field, which is why it works. And this is the secondary winding. There's actually less windings here, which is why we get a lower voltage of 18 volts. So 18 volts is coming out this side, but it's still alternating. So it's going one way, and it's going back the other, and then back this way, and then back this way. So what we're going to do now is we're going to put a fuse on it. So we've got this fuse to keep ourselves safe, because safety is good. And now it comes to our rectifier. Now the way that a rectifier works, you can see that you have voltage is coming in this way. And when it's coming in, it's leaving this direction. Okay? But when it stops and it goes back this way, this is leaving this way. And so you have this constant coming in here and going out here, and coming in here and going out here. And what this device here does is, when this current is coming in this way, when this electricity is coming in this way, these diodes block energy from traveling this direction. So this diode here, the electricity cannot go this way. It cannot. It is blocked. But this electricity certainly can go this way. And so the electricity will come up through this diode and then travel out this wire. And the same goes for this side. When the electricity switches and comes this direction, it cannot go this way. It is impossible for it to go, well, not impossible, but it's not going to go this direction. It's going to choose to go this direction. And it's going to go this way and out this wire. So no matter if the voltage switches and goes this direction, or if it switches and then goes this direction, it's always going to travel through this diode and come this way. Now let's take a look at the negative voltage. So when we have our negative, when we have this changing this direction, this is going to be coming in this way, right? But we need to have a negative terminal. You can't just have electricity flowing in and none coming out. It needs to equalize. There needs to be a circuit. A circuit means a complete path from start to finish. So you can't have a circuit without having a beginning and an end. So we need to have a positive and a negative here. And the way that this works, the way that this rectifier, the reason why it works so well is because when the electricity is flowing in here and it's flowing this direction, this is flowing outwards. And when you have a circuit, and let's say for example we have this circuit and you know it's going to some devices here and it does some stuff, right, and it comes back around and it wants to leave, well, now it's going to come out this wire, and when it comes around to this wire here, these electrons, this electricity is very lucky because these diodes here do not stop them from leaving. When there's positive electricity flowing in here, it doesn't, the electrons that want to leave, they don't want to push against this flow, so they're not going to travel this direction when electricity is coming in this way. So it's going to come up and around, and it's going to come down this way and flow out with this electricity coming out this way to the negative portion of the sine wave of the alternating current, and vice versa. So when the electricity switches and this is now flowing out this direction and this is coming in this way, now this negative is going to come in, and instead of going out this diode, it's going to flow up this way and follow the suction of electrons and come up this way, and the electricity is going to flow out this direction. And so no matter if it wants to push electricity in this way and out this way, or vice versa, in here and out here, it's always going to have one path of leaving and one path of coming in. And this is going to be our coming in, and this is going to be our leaving, and it hooks up with these diodes this way. And that right here is our bridge rectifier. But now we have a problem. That problem is that now we have, see, 18 volts. We have this like this, up here to 18 volts. Now it's coming up and stopping, coming up and stopping, and coming up and stopping. And that's happening 120 times a second, or 120 hertz. And we don't want that. When we try to hook that up to stuff, it certainly can damage things, and it will just not have things operate properly. So the biggest question is here, how do we stop this bump from happening? Well, what we can do here, first what we're going to do is, this item is optional. Not many people have an inductor laying around. I just so happened to pull one out of some electronics that I found literally in a dumpster somewhere. I don't know its Henry value. That's the amount of inductance that it has, Henrys. But what a circuit called for when I was looking online was 30 microhenries. That's what this U is, micro. But regardless, any inductor within reason will work here. And that is what this little device is here. This is a inductor. That's what this is here. These are the diodes, and this is the inductor here. What an inductor does is you have this iron core right here, and you have this coil of wire around it going around in circles and circles and circles and circles, and then it comes back out this way. So you have it coming in here, and it might be coming from your circuit this way, and it might be coming out this way. And when you have these electrons flowing in, or holes flowing in, and I'm not going to get into why they call them holes. It's the positive charges, but for sake of argument, we will say the electricity. So when the electricity flows in this direction and it goes around this coil of wire and then comes back out this way, what happens when it circles around this iron core, it creates an electromagnetic field, and that electromagnetic field is potentially energy. And when you turn off the electricity coming in, there's still potential energy in that magnetic field sitting here, and so it takes a moment for it to die down and flow out. It's essentially like a pond. So if you have a big lake up here and it's draining water down to the ocean out here like this, but you might have a little pond here. And so when you have this lake and it's draining water out this way, and say the lake runs dry, the water comes down, well, it takes a moment for that pond to dissipate that extra water. You know, there was water flowing through it, and whether if, say for example, if you were to have a dam and you were to close the dam and then open the dam and then close the dam and then open the dam, and you were to do that, if you were to open and close it once every 10 minutes, that pond's never really going to get empty. It's going to fluctuate a little bit, but the pond will always have water in it, which means that all of this stream down here is going to continue to have water in it. So that's basically how an inductor works without going heavily into theory. We have our inductor here, and it's resisting the change in electrical potential. That is the best definition that I can think of here. Then, after we have this resistance of change in electrical potential, then we have a capacitor rated at 1,000 microfarads, which, if I'm not mistaken, is 1 megafarad. Don't quote me on that. I'd have to look it up. I should have looked it up before the video, but I did not, and I'm not going to do it right now. But just know that it's 1,000 microfarads. And you can use, depending on the application, you can use a larger capacitor or smaller. Maybe not smaller. I wouldn't use smaller. And what a capacitor does is a capacitor will hold charge in it. So let's say, for example, that we have our positive voltage coming in this direction and our negative voltage here. And this is the negative side. This is the way that a capacitor looks in a circuit. Or it could also be like this, depending on the type of capacitor, but it does not matter for this here. So you have this capacitor, and one side, when you have positive here and you have negative here, what's going to happen is there's going to be an excess of energy on one side, and that's going to want to go to the opposite side of the capacitor that does not have a lot of energy. Energy wants to equalize, and so this is potentially, we're going to have energy particles flowing in here, and we're going to have a whole bunch of energy particles all sitting here, and they really want to go over to this side really bad. They really want to get here, but there is if I'm not mistaken, it's called a dielectric liquid of some type that blocks the flow of these energy particles from flowing to the opposite side. And so you'll end up with this huge potential of energy, and you can have big capacitors with a lot of energy. They make railguns with the capacitors. Capacitors are in air conditioners to help motors spin correct directions. So you're going to have this huge amount of energy here. So let's say we remove this positive and negative, and now it's just blank, like it's not connected to anything. Now you essentially, for lack of a better term, have a battery. It's not really a battery, but you have this storage of energy here that is potential energy. I mean, this wants to go somewhere. This wants to find a path around here or get through this way to equalize. It wants to be equal. So that's what a capacitor is. It's the storage of energy the storage of energy. So now you can see things are starting to come together, actually. We have this changing our current. We have this changing our current from alternating current at 120 volts to 18 volts alternating current. Then we have our fuse for protection, of course. Then we have this little circuit here that is going to change the flow of energy depending on, it doesn't matter if it's flowing in this way or flowing in this way and out this direction. It doesn't matter, because we have it set up to where these diodes are going to only allow it to come in one way and out the other. And to stop it from doing the bumps, the fluctuating, we have this inductor, which helps resist the change in electrical potential. And then we have this capacitor that wants to store this energy here. So it's going to store this energy when that bump comes up, and this kind of equalizes it. It's going to want to store that energy. It's going to flow in here and store it here, while it's going to suck away energy from here and pull it out this way. So that you have this buildup. You have this buildup of, we'll just say, negative energy, and then you have this buildup of positive energy, and you end up having this potential here of energy that wants to go somewhere. It wants to do something. It wants to find a path back around to this side, whether it's through here or around a circuit and back to here. So now you can see that once this charges, which it does not take long, now you will basically have positive charge here and a negative charge here that's not really going to change, because all of the tips here every single one, it's going to charge that capacitor all the way up to here. It's going to charge it up to this very tippy top here. And the capacitor does slowly discharge, and it's going to kind of slant down like this, but then it's going to charge back up to that tip, and it's maybe slowly slant down here, and then charge back up to that tip, just like that. And it's going to continue to do that so that you have this voltage that's 18, 17.8, 17.6, and then back up to 18, and really it's going to... There are peaks inside of this voltage that push it up even higher. I've seen about 21 volts, maybe a little bit more than that. So that's what the capacitor and the inductor do. So now let's take a look at the rest of the circuit here. And you can see now we have this 21 volt positive here, negative here, unregulated, somewhat unstable 21 volt direct current. So now we have successfully used this rectifier to change our current, our voltage from 120 volts alternating to 18 volts direct through this transformer, our full bridge rectifier, through our inductor and capacitor, which filter it and help to maintain a proper stable voltage. And now we have this here. So now you might be thinking, well, what can you do with 21 volts? I can't think of anything that uses 21 volts. Well, regulate that voltage to a usable voltage to something like, say, 12 volts or 5 volts. Your phone charges with 5 volts. You can do things like run LEDs. For example, I have a little test circuit here so that we can test our voltage coming out of our rectifier, our full bridge rectifier circuit here, and we will test to see if we can get some LEDs to light up. And if you're interested to see the circuit for the LEDs, I have this here. So I'll go over this really quickly. We have a voltage regulator, which I will eventually do a video on. So we have our positive rolling in, and typically you would want to, with a regulator, you want to have a capacitor here, but we already have one on our full bridge rectifier, so we're not worried about it. So we're going to have our voltage coming in here. This is naturally going to be connected to ground because a device that does work needs to have a path for energy to travel through so it can do that work. So we have it connected to ground here, and the voltage can travel out this way, current. And we have this regulator. So we have this 21 volts coming in. This 7812 here converts this voltage from any voltage up to 35 volts and as low as 14.5 volts to a stable 12 volts. So now right here we have 12 volts. This is 12 volts right here. And it's going to be stable. Like this can increase or decrease, even though that full bridge rectifier might be, vibrating a little bit because of the alternating current wanting to change. Once it goes to this regulator, it's going to be 12 volts, period. End of story. It's going to be 12 volts. It's not going to fluctuate. It's not going to change. So we're going to have this 12 volts here coming out, and we have this small capacitor here to kind of help to stabilize the voltage. That's the same thing that's happening here. In my case, I'm using a 1 microfarad capacitor. So now we have this push button, which is going to activate our LEDs. When we push this in, it makes a circuit, and energy can flow through here, and it comes across the resistor so that we're not putting an extreme amount of current and voltage through our LEDs. And now we have our LEDs here, and this is safe for 3 LEDs. So I'm going to have a blue, green, and blue LED, and these go through, and we potentially have a negative voltage on this side, or a neutral voltage, and it travels out this way, and that is our test circuit. So we're going to follow our diagram. It's the diagram that I wrote up. Is going to call for 4 diodes. Okay. In my diagram, I'm using a fuse for protection. I would rather use a fuse than not. When we're dealing with 120 volts, we have a lot of energy potential there, and I don't want to hurt ourselves. I don't want to hurt myself. I don't want to have you guys get hurt. So we're going to use a fuse. What I've done with this fuse, and I have soldered on some posts here so that I can plug it into a breadboard. You can see that it fits into the breadboard quite nicely. So we have that fuse there. We're also going to use a capacitor. In my case, I'm going to use a 1000 microfarad 50 volt capacitor, and I'm going to be using an inductor. I have no idea the value of this inductor, but I know that it's an inductor and it's going to work just fine for us here. So first, what we're going to do is we're going to hook up the full bridge rectifier portion of our circuit. So if you remember, we're going to have two diodes facing in towards each other and then two diodes pointing away from each other. And where the pointing away and the facing each other come together, those are the points where our alternating current hooks up. Okay, so it's a little bit difficult to tell here, but I have these two diodes connected here on the same line. So, and they're both facing away. The way you can tell a diode if it's which side's negative and positive, this line's gonna show the output. So our this is where energy comes in, and then it comes out this way. Energy cannot flow back in this direction. So you can see I have this hooked up here, and then this is connected to this rail, which is connected to the back side of this, and this comes out here. And you can see the back side of this is definitely connected here and comes out, and then this is connected to the front of it here. So where our alternating current's going to come into is it's going to come into this rail where this is connected, and it's going to come into the opposite rail over here where this is connected. So next what we're going to do is we are going to plug up our inductor, and we're going to plug up our capacitor. Okay, so you can see here, my inductor, it's going to have energy come in through this rail here, and it's going to come out here. In the same spot where it comes out, where after it's been filtered, I have this capacitor hooked up. So this is going to filter that energy, and this capacitor is hooked up right after this filtering, and this will charge with that filtered energy. So now what we need to do is we need to hook up our fuse. So I am going to hook up my fuse here, and I will just run a wire from the other side of this fuse, from this rail, over to the one of the inputs of this rectifier. Now what I'm going to do is I'm going to run some wire from each component, making sure everything's hooked up. Okay, so everything that I've done here, I've hooked this side of the fuse up to one terminal of our rectifier here, and I have hooked the other side of the rectifier over to here for ease of access with the connector that I have for the transformer. I've also connected the negative side of our rectifier to the negative rail back here. You can see it back here. I have this wire connected to the negative rail where this capacitor is sitting, the negative side of the capacitor. And then I have the positive terminal of our rectifier connected up to our inductor. So now what we have is the positive, which is going to be right here at this rail. This is going to be our rectified and filtered positive right here. So what I'll do for ease is I will connect a little connector here. And the negative is going to be technically right over here, but I can hook up to this negative rail so that they're a little bit closer together, so it's a little bit easier. And now we have our positive and our negative coming out of our full bridge rectifier and filter. So now what we can do is we can take a look at this with a multimeter and see exactly what it's doing. So now you can see here I have my multimeter in shot. So I'm going to go ahead and hook up my negative terminal to the power rail here. I'm using my pen probe that I made from a previous video to do this demonstration. Okay, so I have my transformer hooked up. So let's probe around and see what kind of voltages we get here. So I'm checking for DC voltage, you can see here, and I'm just going to, I have it connected to negative ground. I'm going to plug in here at the other side of the rectifier. You can see I'm getting 20.26 volts. Let's see what happens if we remove our capacitor when it's not charging it up. 6.885 volts. You can see that voltage definitely drops down. And you can see I get a weirder fluctuating lower voltage. Okay, so let's go ahead and plug our capacitor back in and watch what happens when I do. 20.1 volts. You can see our capacitor is actually charged up with energy, and so we can actually demonstrate this here. If I take this out and I plug it into the breadboard, you can see a little spark. It's full of energy. You can see I can charge it up. If I come over here, you can see when I plug it in, I'll do it one more time for you guys. That spark, it's actually full of energy. So we'll leave it plugged in there so that it's helping to clean our signal. And you can see we got 20 volts coming out. That is perfect. So now, let's do something with it. So we're going to come over to our demonstration board here where I have these LEDs set up. And all I'm going to do is plug this negative into the negative side here, and the positive to the positive side. Once I have this energy traveling in here, let's see. This side the voltage will drop slightly. You can see it's just below 20 volts. That's because there's a slight load on it and that voltage is going to drop slightly, but that's okay. You can see this device here. This is what actually changes the electricity from a higher voltage down to 12 volts regulated. So you can see when I plug into one side of this, we have that 20 volts coming in. And when I plug into the middle terminal, it's plugged into ground. When I plug into the output terminal, you can see 12.15 volts. This is regulating our voltage from 20 volts to 12 volts. We can run LEDs like so. Nice, regulated, filtered 12 volt signal that was once coming in through our wall at 120 volts AC and is now coming out at 12 volts DC. Alright guys, I really hope you enjoyed this video. I enjoyed making it and demonstrating these things and actually building the concept circuit. I'm sorry it was a little bit longer, but it has a lot of juicy meat and potatoes understanding kind of stuff in it, so that's always good to have. If you guys want to see more stuff like this, then let me know. Post down in the comments. Tell me things that you liked, things that you didn't like. If you want me to shut up sometimes, let me know. If you want me to explain some more stuff, let me know. I don't know until you tell me. So, again, thank you guys for watching if you lasted this long, and I hope to see you guys again. I'll see you next time. Peace out!